Hey folks, it's me again. I am back. This is lesson 5 in the Matter and Energy unit posted to Google Classroom. So we've looked at now the differences between physical changes and chemical changes. Now we're going to look more at chemical changes. Specifically, there's 4 different types of chemical reactions you need to be able to identify. So quickly, as a review of the lesson 4 concepts, for this first process, is this a physical or a chemical change? And then same thing for the second process, is it a physical or chemical change? So I do want you to write down an answer in your notes. I will be checking when I check your submission that you have answered these 2 questions. Okay, so just ID, you could just circle physical or chemical for both of those. So as a reminder, a chemical change is a process where you have the making or breaking of bonds. So the formulas at the end of the process are different from the formulas that you started out with. Also, when you are making observations of processes, you can tell if something is a chemical reaction or chemical change by certain observations. One of those observations is evolution of light or heat. So if you feel something, if you feel a container getting warmer during a process, or even getting colder, right? So it could absorb or release. Or if there is light given off, you know that there's a chemical change happening, like combustion. Production of a gas is another way to tell if a chemical reaction has occurred. And there's two different ways to tell if a gas is being produced. One of those is by looking for bubbles. So let's say you had a solid that you dropped into a liquid, and you had bubbling occur, you know that a gas is being produced. Or if you can smell or waft an odor, you know that it's a gas, right? You can only inhale gases, you can't inhale liquids. We know that that's called drowning. Another way that you can tell that a chemical change is occurring is through the formation of a precipitate. Now, this is a word that you will see more, as we progress through the year. So if you think about the weather and what is precipitation is stuff that falls from the sky, right? It could be rain, sleet, snow. So in a chemical reaction, a precipitate is a solid that forms during a reaction. I abbreviate reaction RXN, just so you know. So solid that forms during a reaction, usually between 2 solutions. And I will explain that between 2 solutions. I'll explain that further as I give you examples of types of reactions. And the last one would be something like a color change. So if you think of rusting, right? Iron starts out as a silvery gray color and rust is reddish orange. That would be an indication that a chemical change has occurred. So for chemical reactions, you can classify them based on the format that they take. So when you look at the equation and you look and see what's on the left-hand side of the arrow and what's on the right-hand side of the arrow, you can put reactions into one of 4 different categories. Of course, there's plenty more than this, but for now, we're looking at 4 different types of reactions. The first one we'll look at is synthesis, decomposition, synthesis, decomposition, single replacement, which sometimes you will see as single displacement, same deal, and then double replacement or double displacement. I tend to use the word replacement, and the Regents tends to use the word replacement. Sometimes, though, if I'm using materials from other sources, they will say displacement, but it refers to the same thing. So first of all, we're going to look at a synthesis reaction. So a synthesis reaction is when you have multiple reactants. Remember, reactants are on the left. That's what's reacting. And you have a single product. So it will take the format of A plus B producing AB, or if you had 3 multiple reactants and a single product. Okay. There's nothing else really to add to that third bullet. So these three are just examples of synthesis reactions that are down here. So this first one, this would be the synthesis of water, right? Hydrogen plus oxygen gas produces water. This would be the formation of rust. Iron reacts with oxygen in the atmosphere to form iron 3 oxide. And this is what happens when you carbonate water. So when you make a carbonated beverage, sodas, seltzers, right? The CO2 gets pushed into the water, and some of it will react with the water and form what's called carbonic acid. So those are all synthesis reactions. There's obviously plenty more. We will be doing a lab where you're going to be seeing all 4 of these types. So if we're talking synthesis is putting together, right? If you synthesize, right? Put together. The opposite of putting something together is taking something apart. And that would be a decomposition reaction. So in a decomposition reaction, you would have a single reactant and you would have multiple products. My kids are coming up the steps. They're going to interrupt. Stay tuned. So single reactant and multiple products. So single reactant, break apart. Single reactant, multiple products. Okay, so here would be examples of those. So taking water molecules can be decomposed using electricity into hydrogen gas and oxygen gas. The decomposition of calcium carbonate. This is, no, I can't think of I was going to give a different example. It doesn't work there. Sorry. But this is called calcium carbonate. It decomposes into calcium oxide and CO2 gas. And this is called sodium azide. It breaks down into sodium and nitrogen gas. This process happens in an airbag. So if an airbag deploys, it inflates with nitrogen gas. So this, I have a video. I'm not sure if it's going to work. If not, I'll show you in class. But this just goes through a few examples. It's not going to work. I tried to embed it, but Grandma had trouble with her technology today. Okay. Next type of reaction is a single replacement or a single displacement reaction. So this one is a little, not trickier, but you need to look at it a little more closely. So with a single replacement reaction, you're going to have 2 reactants and 2 products, but they're going to take on a certain format. Okay, so you're going to have on your reactant side, you're going to have a compound that is, made up of 2 or more elements. You're going to react it with a single element, and there's going to be a switch that occurs. You'll end up with a new compound, and it will free up one of the elements that were in the original. Okay, so I'll explain this and give you examples. So the 2 different options you have are a metal can replace a metal, or a non-metal can replace a non-metal. I like to think of this as an upgrade reaction, and I will show you what I mean with this. So the format this can take on is you can have a compound, right? Compound, 2 different elements, react with an element, and what would happen is B would come in and replace A. So now the new compound would be BX and A would be left out. Another option would be if you have your compound, so this is showing metal replacing metal, because in compounds, metals are always listed first, right? So would be a metal, this would be a metal, this metal comes in and replaces the one that was there. Or you could have a non-metal replacing a non-metal, and the same kind of thing would happen. So in this case, Y and X would be nonmetals, and Y could replace X. You can't have a metal replacing a non-metal, so I couldn't have B come in and kick X out because I can't have two metals partnered up together to form a compound. So I call this an upgrade reaction. I think I have this on the next slide. Okay, because the replacement can only occur if the single element that's sitting there is an upgrade from the one that is there. So there's a reference table that will help you out with this. I'm not going to get too far in depth with the reference table at this point in the year, but it's list, and top to bottom, they're more active and less active. So think of it this way. Here's you. Look how cute you are. Look at your cute little hat. And you have a cell phone that has a busted screen, and the phone's like a few years old, and you get some money for the holidays, and you're like, I need to go to the store and get a new phone. Okay, so the combination that exists here is kid and old phone. Okay, so you go to the store, and on display in the store, they have a bunch of different options. They have a flip phone, which of course that was the first phone that I had, not even in the 1900s. Anyway, I'm old. You would have like some sort of, cricket phone that has like two buttons on it. And then you have like the iPhone Infinity Plus, whatever option it is, but it's like, there's an angel choir singing. It has like spotlights on it. It's like super fancy. Okay, so we're gonna call this new phone. So when you go to the store and you're partnered up with your old phone, and then this new phone is here, if the single element, so thinking about this back in terms of a reaction, if the single element is an upgrade from the similar substance in the compound, right? So I'm not going to replace myself with a phone. I'm not going to like kick myself out and I'm going to sit on this recycling bin or whatever. I want to replace phone with phone. If the single is an upgrade from the one that's already bound in the compound, it will kick it out. So as a result, you will have yourself leaving the store with a much bigger smile on your face and a lighter wallet, but you will have like this gorge new phone that you'll immediately like put a case on because your family will kill you if you break it. And then the other one that was kicked out gets scrapped for parts. So the new products would be kid with new phone, and then the old phone gets trashed. Okay, so we have a compound plus an element. We produce a new compound because we've replaced one of the elements with the one that was free, and we kick the old one out. These are 3 examples of single replacement reactions. It uses reference table J, which again, I will explain what that is at a later time. But you can look at the format here. I have a single element. I have a compound, right? This compound is silver nitrate, has a polyatomic that functions as a unit. The copper is more reactive on this reference table than silver is. So it's like the new phone situation. Oh yes, it can swap in and it can kick out the silver. So the silver is by itself and the copper is now with the nitrate. So let me read this, what this would say in words, and you can hear it. You can hear the replacement. Copper plus silver nitrate produces copper 2 nitrate plus silver. Okay, we have a single element got replaced. This one, same kind of idea. Zinc plus copper 2 nitrate produces copper plus zinc nitrate. So these compounds, this silver nitrate and the first one, and this copper 2 nitrate, these would be solutions. So these compounds are soluble in water. So I would have, like in the second example, I would have a beaker where I put copper 2 nitrate powder and I dissolved it in water. Okay, and when that happens, the copper and the nitrate are just like floating around in there. I would then take a piece of zinc metal and I would drop that piece of zinc metal into that beaker. What would happen is the zinc would turn into ions and float around with the nitrate, And the copper ions that were floating around would turn back into copper metal, that you would actually see that reddish brown metal. I will show you a demonstration, not this exact one, but something very similar of how this looks, because it's pretty cool. You can see it very, very easily. This example is with a non-metal option. So we have chlorine gas, and chlorine is a non-metal. So in this compound of potassium iodide, the metal comes first, the non-metal comes second. So we would have a replacement occurring with the chlorine and the iodine. Look to see what type of element the single element is. If it's a metal, you're looking for the metal in the compound to see if a replacement can occur. But if the single element is a non-metal, you're looking for a non-metal from the compound to replace. So in this case, chlorine plus potassium iodide would produce potassium chloride, and then iodine would get kicked out. So again, I will explain those further in class, but that's what they look like. The last type of reaction is called a double replacement reaction. So a double replacement reaction, I don't know if this reference will even make sense to you, but there's a show that was called Wife Swap, or Trading Spouses, where you would have like a family who lives in like Beverly Hills, and they would have like a family who lives in, middle America, and they would swap moms for a week, and they would have to like teach the family their routine and stuff. It was terrible. But the idea of this double replacement reaction, it will look like that. You will have these partners, these two sets of partners that trade partners. So for this reaction, you will have ions of two compounds exchanging places in an aqueous solution. And they will form two new compounds. Okay, one of the products would be a precipitate, which is a solid or a gas or water. And it would show you that like in the symbols. So it would say S or G, or water would actually be a product in it. So the format that these would take, you will have two compounds on the left and two compounds on the right. So look and see what happened here with the switching. A was partnered up with X. B was partnered up with Y. And when the switch occurs, A is partnered up with Y and B is partnered up with X. So generally speaking, all you're going to do is you're going to take the first member of each couple and just swap them with each other. So they're partnered up with their opposite. The next three slides, the last three slides, are going to show you three examples. So this is the first one. So let me say what this reaction is with words, and you will hear the switching. So I have a solution. Let me zoom in here. I have a solution of silver nitrate. I have a solution of sodium chloride. So I would have a beaker, and in that beaker, I would have silver nitrate dissolved in water. I would also have sodium chloride in another beaker dissolved in water. Okay, what I would do is I would combine them, okay, and I would pour them together into the same beaker. What ends up happening is, so I have silver nitrate plus sodium chloride, I end up with sodium nitrate and then silver chloride. The sodium nitrate would stay dissolved in the solution, but the silver chloride would actually fall to the bottom of the container as a solid because that compound is not soluble in water. Okay, so that forms what's called a precipitate. It would go the whole container would look cloudy, and then the silver chloride would settle out to the bottom. And again, you will see this when you do a lab, and I'll show you some examples as well. Second example I have here, this one's a little bit different. You'll learn more about this particular type of double replacement when we do acids and bases. So, but look at how the partnerships work out. We have hydrogen and chlorine, we have magnesium and hydroxide. The switch that occurs is the magnesium now is partnered up with the chlorine, and it forms then water. And you might be like, well, where's the partnership there? It should be H and OH. But look, you can rewrite H2O is HOH. It's still H2O, but then you can see the hydrogen from the acid and the hydroxide from the base. But that one forms water, and so that's another type. This is called also known as a neutralization reaction, because you have an acid plus a base reacting together. Again, you'll see this in more detail later in the year, that particular type. Last type, we have silver nitrate. I'm sorry, not silver nitrate, lead 2 nitrate, which is a solution. We have potassium iodide, which is a solution. When I pour those 2 containers together, the one compound, potassium nitrate, is soluble, but the other compound, lead 2 iodide, is not. I think this one is yellow. I'll have to see if I have these at school to show you, but I think that compound is yellow. So you would have a clear solution, you would have another clear solution, you would pour them into the same container. This would stay dissolved and it's clear. This solid stuff would eventually settle to the bottom. You would be shown that it's a precipitate, okay? So again, we have 4 different types of reactions that we've looked at. We have looked at synthesis reactions, which is when you put elements together, or multiple reactants together to make a single product. Decomposition is the opposite, where we have a single reactant breaking down into multiple products. And then we have single and double replacement. Single replacement, we have a single element reacting with a compound to form a new compound and a new single element. Double replacement, we have a 2 sets of partners, right? Compound, and then 2 new compounds that form after they switch partners. And that is it.